Hi everyone, and thanks for coming to our talk. My name is Arjun Lakshmipathy, and today I'm excited to share our aptly named in light of COVID-19 paper, Contact Tracing, a low-cost reconstruction framework for surface contact interpolation. This is joint work with my advisor Nancy Pollard and colleague Dominic Bauer at Carnegie Mellon University. Hand post tracking and motion recovery techniques have garnered considerable interest in the robotics and graphics research communities, especially in the past several years. These efforts have led to a number of advancements in manipulation, learning from demonstration, VR, AR, and animation. But most of the current research efforts do not consider points of contact. Our belief is that contacts provide valuable information that can greatly supplement existing techniques. And this is understandable to some extent because object surface contacts are difficult to capture and even to reconstruct. These contacts constantly change, are occluded from vision-based tracking methods, are altered and difficult to reconstruct from tactile sensing gloves, and are further complicated by the natural complexities of the human hand. But capturing and tracing these contacts would yield valuable information. With it, we could teach manipulators not just how to perform single grasps, but entire custom manipulations. And because these contacts are not strictly tied to the original manipulator morphology, we could theoretically use it to train non-anthropomorphic hands as well. And the applications here are practical. Consider some of the tasks we do every day. In the case of a tool such as a flashlight or a pencil, we use one grasp to first pick up the object and then reorient it in hand in order to actually use it. In the case of a book on a shelf or a dish in a cluttered dishwasher, we use one grasp to maneuver the item out of the cluttered space and then reorient it to a new grasp in order to transport it in a stable manner. Fortunately, as Brumbuth and colleagues demonstrated, it is possible to capture ground truth contacts in static grasps using thermal imaging. The results are superb, with the only downside being the high cost of thermal cameras. In today's talk, I will present a framework that builds upon this work, enabling capturing of these contacts at substantially lower costs and, more importantly, a method of reconstructing intermediate contacts for simple manipulations. To start, we define a simple manipulation as one in which the grasps at the beginning and end of the manipulation are distinct. In the case of this book, the initial grasp would be that used to maneuver it out of the cluttered shelf, and the final grasp would be that used to transport it stably. Additionally, the transition from initial to final grasp must be direct and done in hand. We interestingly found that many of these manipulations involve straight-line motions. In the case of this box demonstration, the thumb slides directly from its initial to final position straight along the back of the box. And it turns out this is consistent with the thermal manipulation trace. Observations like these eventually became the core building blocks of our interpolation algorithm. But of course, there are some more nuances, which I will explain in more detail later. With that, let's start with our scanning procedure. Thermochromic paint is a low-cost alternative to thermal imaging that exposes thermal signatures to standard RGB cameras. With it, we were able to use a single Intel RealSense, capture at a substantially higher resolution, and completely skip camera calibration and image registration. To make our lives easier, we deliberately selected a pigment with a high color contrast calibrated to a low transition temperature, and mixed the pigment with acrylic clear gloss in order to bind it to standard PLA material. When comparing the two approaches, we found there was no observable information loss in the signature, and the problem of heat dissipation was consistent in either imaging process. After 3D printing and spray painting a number of objects, the remainder of our scanning procedure largely followed that of prior work, including depth map segmentation, point cloud registration, and vertex color reconstruction using several snapshots of the object rotated on a turntable. We repeated this procedure twice in order to generate reconstructions of both the initial and final grasps. Next, let's dive into the processing pipeline. Over the course of several preliminary studies, we noticed 4 emergent behaviors in simple manipulations. First, as can be seen across all the demonstrations here, fingers slid relatively straight along the object's surface from initial to final grasp position. Second, as can be seen in the pinky about halfway through the lemon demonstration on the bottom left, contacts were occasionally removed mid-manipulation, but removed from their initial point of contact. Third, as can be seen in the palm in the box demonstration on the bottom right, contacts were also occasionally added mid-manipulation, but added to their final grasp positions. And fourth, none of these events were really disjoint. They all just occurred at some point during a smooth natural motion of the hand. And these observations are what led to the three core conjectures of our interpolation algorithm. First, that patch movements are synchronous. Second, that assuming a simple manipulation, the paths of these contact patches can be traced linearly in accordance to the object's surface geometry. And third, that patches can be added or removed abruptly at any point during the manipulation. In the next few slides, I'll describe the process for converting these contact maps into the representation used to perform the interpolation. First, we annotated and labeled each patch region. In the scope of this work, we did this process manually in order to ignore the impact of noisy artifacts generated during the scanning procedure. Next, a single vertex within each patch region was designated as the patch root. This root has no physical meaning. It is merely a bookkeeping item used to designate the interior from the exterior of each patch during the interpolation. From these roots, we then computed the patch boundaries. Note that these boundaries are tight. It is impossible to move from any vertex within a patch interior to a vertex outside the patch without crossing at least one vertex in the boundary set. And we did this to make sure that a flood fill originating from the patch root is guaranteed to terminate. Doing this for both the initial and final scans gave us a collection of patches that were both agnostic to shape and underlying object geometry. And from this, we could easily map the correspondence between the two sets. To begin the tracing process, we first merged each patch collection onto the same mesh. Unfortunately, this representation was not quite sufficient for doing a point-to-point interpolation because the number of vertices in each boundary set was almost never equal. So to resolve this, we downsampled each boundary at roughly equal arc length increments in order to produce an equal number of representative points, which we called the interpolation boundary. To complete the correspondence, we designated a cycle order for each boundary set and then mapped the roots directly to one another. And with this full correspondence, we could now perform a linear interpolation between each pair of interpolation boundary and root sets. But to generalize to any object, the trace had to work for arbitrary triangle meshes. In other words, the straight line approximations instead had to extend into surface-conforming geodesic paths. Fortunately, it turns out you can find geodesic paths in triangle meshes by just flipping edges. Under the hood, the edge flip algorithm performs these flips over an intrinsic triangulation of the mesh, which can be thought of as effectively tightening a shortest path over the original mesh graph. The geodesic paths can then be chopped up into arbitrarily small increments for any choice of dt. To recreate a patch in an intermediate state, we first need to find the intermediate boundary, which we can do by performing a bidirectional breadth-first search from each interpolation boundary point to its cycle-adjacent neighbor. Filling in the entire patch is then just a matter of doing a flood fill starting from the root. And if we repeat this for every single point along the geodesic paths for all patches, we can effectively trace the contacts for a full simple manipulation. Well, almost. It only works if correspondences actually exist between the initial and final scans. But you may remember that one of our core conjectures was that contacts could be arbitrarily created or destroyed mid-manipulation. In this example, we can see that a palm contact is present on the final scan, but totally absent from the initial scan. So how do we fix this? Well, you may remember from the preliminary studies that I mentioned contacts were either added to their final position or removed from their initial position. So why don't we start by using the scan that we do have contact information for? Then, if the contact was added mid-manipulation, we can instead grow it out from the root. And if it was removed, we can collapse it down to the root. And to make sure that this accounts for arbitrary time steps, why don't we threshold it with a step function so that the collapse or expansion can occur instantaneously at any select point in time? The result looks kind of like this. With this modification, we now have a framework that accounts for patches of arbitrary shape, arbitrary underlying triangle meshes, and can deal with missing patch correspondences. So despite its simplicity, it gives some pretty neat results, as you can see in some of these demonstrations. Now, I did mention that this framework only works for simple manipulations. But what if we could extend it to more complex manipulations? It turns out there's a very elegant way to do this through simple keyframe subdivision. In other words, rather than only having 2 scans, we can extend that to instead n scans, where each I to I plus 1 scan can be approximated as a simple manipulation. Here's such an example where we do that with 3 scans instead of 2. And I did mention at the start of this talk that this data could be useful in training manipulators that are not necessarily anthropomorphic as well, even if the original demonstration was done by an anthropomorphic hand. So, to wrap up the experiments, we decided to put this to the test by transferring a demonstration done by a human hand to a tendon-driven simulated soft robot hand with a considerably different morphology using reinforcement learning. But it is worth noting here that we did not encode any information about object rotation into the reward function. Instead, we only instructed the non-anthropomorphic hand to reach for the contact points over the entire time series, and it turns out that naturally resulted in the manipulation we were going for. Of course, simplicity often comes with the trade-off of accuracy, and it would be a little bit overreaching to say that our interpolation framework generates a perfectly accurate reconstruction. As can be seen in the example here, however, the thumb trace on the right generated by our framework is actually a very good match for the thermal trace recorded from the full manipulation. But in the pair of examples on the left, there are some noticeable divergences. Our interpolation framework suggests that the finger traces thin out towards the end, but on the actual thermal trace, they appear to be more full-bodied. But despite the differences, this kind of framework is still a very important first step in eventually generating even better and more accurate reconstructions moving forward. And thus, a natural next step for this work would be to leverage the estimates of our interpolation framework with existing tracking methods. If, for example, we could fuse the readings of a tactile sensor glove with the estimates of our algorithm, we could not only produce more accurate reconstructions, but potentially eliminate the need for keyframing, which, while reasonable in theoretical formulation, is impractical to implement in large scale, especially for very complex manipulations. So in summary, we have presented a novel, low-cost reconstruction framework for surface contact interpolation that can deal with multiple contacts and is agnostic to patch shape and underlying surface geometry. We have also introduced a simple extension of the framework to account for more complex manipulations and demonstrated the value of this information in the training of a simulated soft robot hand. In the future, we hope to leverage this work in creating even more accurate reconstructions and eventually building out a large data set of contact time series data. We hope that this kind of data set would be useful in training manipulators in a wide variety of contexts. Thanks for watching, and I look forward to speaking with you at the Q&A.